On August 13, 1941, at Peenemünde West Airfield on Germany's Baltic coast, test pilot Heini Dittmar prepared for what appeared to be a routine-powered flight in the Me-163, a V-4 prototype. The aircraft represented the culmination of Alexander Lippish's revolutionary approach to interceptor design, a tailless, rocket-powered fighter capable of climbing to 30,000 feet in under 3 minutes. The Walter HWK 109-500, a rocket motor, had been tested extensively in static trials, producing 1,650 kilograms of thrust through the controlled reaction of T-STOF and C-STOF propellants. Ground crews had loaded the fuel tanks according to established procedures, with T-STOF occupying the main tank and C-STOF, stored in separate compartments to prevent premature mixing. All instruments indicated normal conditions. The flight authorization had been approved by the test program leadership. Nothing in the pre-flight sequence suggested that this aircraft design would eventually destroy more of its own aircraft through operational hazards than it would ever eliminate enemy bombers. The Me-163's fundamental design philosophy emerged from a convergence of technological opportunity and strategic necessity that characterized German aviation development in the early 1940s. Professor Alexander Lippisch had spent the previous decade refining tailless aircraft configurations, believing that eliminating conventional empennage would reduce drag and improve high-speed handling characteristics. His work with the DFS-194 glider had demonstrated that swept-wing tailless designs could achieve stable flight, though with handling characteristics that demanded precise pilot technique. When the Reich Air Ministry sought interceptor designs capable of reaching Allied bomber formations operating at previously untouchable altitudes and speeds, Lippisch's tailless configuration appeared ideally suited for rocket propulsion integration. The selection of Walter's rocket motor technology represented a calculated engineering trade-off that would define every subsequent operational characteristic of the Me-163. Helmuth Walter had developed hypergolic propellant systems that eliminated the ignition complexity plaguing early rocket designs. T-STOF, consisting of 80% hydrogen peroxide stabilized with oxyquinoline, served as the oxidizer. C-STOF, a mixture of hydrazine hydrate, methanol, and copper catalyst, functioned as the fuel. When these substances contacted each other, they ignited spontaneously without requiring external ignition sources, producing thrust almost instantaneously upon valve opening. This hypergolic characteristic promised reliability advantages over spark ignition systems, particularly during combat maneuvering when conventional ignition systems might fail due to G-forces or mechanical stress. However, the chemical properties that made T-STOF and C-STOF attractive for rocket propulsion also created operational hazards that extended far beyond the combustion chamber. T-STOF's high-concentration hydrogen peroxide was inherently unstable, decomposing rapidly when exposed to catalytic materials commonly found in aircraft construction. Copper, iron, and various organic compounds could trigger decomposition reactions that generated superheated steam and oxygen at pressures capable of rupturing fuel lines and tanks. C-STOF's hydrazine component was both highly toxic and prone to forming explosive vapor concentrations when spilled. More critically, any accidental mixing of T-STOF and C-STOF outside the combustion chamber would produce immediate uncontrolled combustion, impossible to extinguish with conventional fire suppression methods. The design team's approach to managing these chemical hazards reflected engineering assumptions that would prove fundamentally inadequate under operational conditions. Fuel system architecture prioritized positive segregation between T-STOF and C-STOF through separate tankage, independent feed lines, and sequential valve operation. Tank construction utilized materials selected for compatibility with the respective propellants, with special attention to eliminating catalytic metals from T-STOF system components. Fuel loading procedures specified precise timing and sequence requirements to minimize handling duration and prevent cross-contamination. Emergency jettison systems provided rapid fuel disposal capability should abort become necessary during flight operations. These design decisions embodied several critical assumptions about operational reality that subsequent experience would challenge. The first assumption held that ground crews could consistently execute complex fuel handling procedures under operational pressure without making errors that might result in propellant mixing or contamination. The second assumption presumed that aircraft materials and components would maintain their chemical compatibility with hypergolic propellants across the full spectrum of operational stresses, including vibration, temperature cycling, and combat damage. The third assumption expected that fuel system purging and jettison procedures could reduce propellant residues to levels safe for routine maintenance and ground operations. Perhaps most significantly, the design philosophy assumed that the benefits of hypergolic ignition reliability would justify accepting the operational complexities associated with handling substances that became explosively dangerous when accidentally combined. This assumption reflected a broader engineering culture that emphasized technical performance over operational safety margins, viewing complex handling requirements as acceptable trade-offs for superior combat capability. The Mi-163's designers believed that proper training and procedural discipline could manage chemical hazards that were inherently unforgiving of human error. The aircraft's control systems and pilot interface design reflected similar assumptions about human performance under stress. The rocket motor's thrust characteristics provided acceleration capabilities that exceeded anything previously experienced in aviation, potentially subjecting pilots to G-forces that could impair consciousness and decision-making ability. Yet the cockpit layout placed critical fuel system controls in positions that required precise manipulation during high-G flight phases. Engine shutdown procedures demanded rapid, sequential valve operations that became exponentially more difficult as acceleration forces increased. The instrument panel provided limited feedback about fuel system status, offering flow indicators and pressure gauges, but no direct measurement of propellant mixing ratios or contamination levels. Landing system design exemplified the consequences of prioritizing performance over operational safety margins. The Mi-163's high landing speed, combined with its limited fuel capacity, meant that powered approaches were impossible. Pilots had to execute unpowered gliding approaches similar to modern gliders, but at speeds nearly double those of conventional gliders and with far less favorable glide ratios. The retractable skid landing gear eliminated the weight and complexity of conventional landing gear, but provided no shock absorption capability and demanded precise touchdown attitudes to prevent structural damage or loss of control. These design characteristics created operational conditions where minor deviations from optimal procedures could escalate rapidly into catastrophic failures. A slightly contaminated fuel tank could trigger decomposition reactions during loading. An improperly purged fuel line could explode during maintenance. A marginally high approach speed could result in landing gear failure and potential fuel system rupture. An engine shutdown sequence executed too slowly during high-G maneuvering could result in propellant mixing and cockpit fire. Each operational phase contained decision points where small errors carried disproportionately severe consequences. The regulatory environment surrounding the Mi-163's development provided insufficient oversight of these safety implications. Test program protocols focused on demonstrating performance capabilities rather than systematically evaluating operational risk factors. Flight test procedures emphasized achieving design speed and altitude targets rather than exploring failure mode characteristics or emergency procedure effectiveness. Safety assessments concentrated on preventing catastrophic structural failures during high-speed flight rather than examining the cumulative risks associated with routine ground operations, fuel handling, and maintenance activities. This regulatory approach reflected broader institutional assumptions about acceptable risk levels for experimental aircraft programs. Military aviation culture traditionally accepted higher loss rates for combat aircraft than would be tolerable in civilian aviation, particularly for aircraft intended to operate in extremely demanding tactical environments. The strategic importance of developing effective interceptor capability against Allied bomber formations created pressure to accept operational risks that might otherwise trigger program cancellation or fundamental design revisions. The engineering documentation produced during the Mi-163's development reveals the systematic nature of these flawed assumptions. Technical specifications emphasized propellant performance characteristics and thrust-to-weight ratios while providing minimal analysis of fuel handling risks or emergency procedure effectiveness. Test reports focused on achieving speed and climb rate objectives rather than documenting fuel system safety margins or pilot workload during critical phases. Training materials concentrated on normal operating procedures rather than emergency management or chemical hazard recognition. The cumulative effect of these design assumptions created an aircraft that functioned exactly as intended while simultaneously violating fundamental safety principles that govern successful operational aviation. The Me-163 achieved unprecedented performance through design decisions that made routine operations inherently dangerous, creating conditions where even experienced pilots operating according to established procedures faced unacceptable failure probabilities. The aircraft succeeded technically while failing operationally, demonstrating capabilities that could not be safely exploited under real-world conditions. The operational complexities embedded within the Me-163's design created a web of latent conditions that systematically degraded human performance precisely when precision was most critical. Training protocols developed for the aircraft reflected an institutional understanding of aviation that had evolved around conventional propulsion systems, where procedural errors typically produced gradual degradation rather than immediate catastrophic failure. The hypergolic fuel system demanded a fundamentally different approach to human factors management, yet training doctrine continued to emphasize techniques suitable for aircraft where mistakes offered opportunities for recognition and correction. Pilot selection criteria for the Me-163 program prioritized experience with high-performance aircraft and demonstrated ability to handle unusual flight characteristics. Test pilots like Heini Dittmar brought extensive backgrounds in glider operations and experimental aircraft evaluation, providing essential skills for managing the aircraft's challenging landing requirements and unconventional control responses. However, the selection process could not account for the psychological adaptations required to operate an aircraft where routine procedures carried life-threatening consequences. Traditional aviation training taught pilots to develop intuitive responses to common situations, but the Me-163's fuel system created conditions where intuitive reactions could trigger explosions. The fuel loading process exemplified how operational realities conflicted with design assumptions about human performance reliability. Ground crews received training on proper handling sequences for T-STOF and C-STOF, including specific procedures for avoiding cross-contamination and managing spill situations. Technical documentation specified precise timing requirements for each step of the loading process, with particular emphasis on completing T-STOF loading before beginning C-STOF operations. Emergency procedures provided protocols for immediate area evacuation should accidental mixing occur during ground operations. However, the operational environment systematically undermined the conditions necessary for consistently executing these procedures. Combat readiness requirements created pressure to minimize ground turnaround times, compressing the duration available for careful fuel loading. Multiple aircraft operations at single facilities meant that ground crews often worked simultaneously on several aircraft, increasing opportunities for procedural confusion or material cross-contamination. Weather conditions frequently forced ground operations to proceed under circumstances that compromised visibility and manual dexterity. Equipment shortages sometimes necessitated improvised solutions that deviated from standard procedures. More fundamentally, the fuel loading process demanded sustained attention to detail over extended periods, while handling substances that provided no margin for error. T-STOF loading required constant vigilance for signs of decomposition, including unusual heating, vapor generation, or pressure increases that might indicate catalytic contamination. C-STOF handling demanded precise measurement and transfer techniques to prevent spillage that could create explosive vapor concentrations. The sequential nature of loading operations meant that errors made early in the process might not manifest until later stages, when corrective action could be impossible without complete fuel system purging. Human factors research conducted decades after the Me-163 program would demonstrate that sustained high-precision performance, under time pressure, represents one of the most demanding cognitive tasks humans can attempt. The combination of complex procedures, unforgiving consequences, and operational stress creates conditions where even experienced personnel experience degraded performance. Yet the Me-163's operational requirements demanded exactly this type of sustained precision from ground crews who often worked extended shifts under combat conditions. Cockpit design reflected similar misunderstanding of human performance limitations under the extreme conditions the aircraft created. Control placement followed conventional aviation practice, with primary flight controls positioned for easy access and fuel system controls located according to their operational priority. The instrument panel provided standard pressure and flow indicators for monitoring fuel system status. Emergency controls included fuel jettison systems and engine shutdown mechanisms designed for rapid activation during crisis situations. The physical demands of rocket-powered flight challenged these design assumptions almost immediately. The Walter rocket motor's thrust characteristics produced acceleration levels that exceeded human tolerance for sustained consciousness. During climb phases, pilots experienced G-forces sufficient to impair vision and motor coordination, precisely when fuel system monitoring became most critical. The instrument panel layout that seemed logical during ground testing became difficult or impossible to read when acceleration forces prevented normal head movement or eye focusing. Engine shutdown procedures illustrated the consequences of these human factors oversights. Normal shutdown required sequential valve closure in specific timing to prevent propellant mixing in fuel lines. The procedure demanded precise control manipulation while maintaining aircraft attitude and airspeed within narrow parameters. However, high G acceleration during climb phases made fine motor control extremely difficult, while the rapid altitude gain compressed the time available for executing shutdown sequences. Pilots found themselves attempting to perform precision manual tasks while experiencing physiological stress that degraded their ability to complete those tasks successfully. Emergency procedures presented even more challenging human factors problems. Fuel system failures during flight required immediate recognition of subtle indicator changes while managing aircraft control under rapidly changing conditions. The distinction between normal operational variations and dangerous system malfunctions often depended on recognizing small differences in pressure readings or flow rates. Yet the cockpit environment during rocket-powered flight included noise levels, vibration, and acceleration forces that interfered with normal sensory processing. Communication systems between ground crews and pilots created additional human factors vulnerabilities. Radio protocols for fuel loading coordination required precise terminology to distinguish between T-STOF and C-STOF operations. Ambiguous communications could result in ground crews performing incorrect procedures or pilots receiving inaccurate fuel status information. The time-critical nature of rocket aircraft operations compressed communication windows, increasing pressure for abbreviated radio calls that might omit essential safety information. Weather conditions significantly amplified these human factors challenges. Rain or snow created additional hazards when handling T-STOF, as water contamination accelerated decomposition reactions. High winds during fuel loading increased spillage risks and made precise measurement more difficult. Cold temperatures affected fuel handling equipment function and ground crew manual dexterity. Limited visibility during dawn or dusk operations made it difficult to detect visual signs of fuel system problems or contamination. The training infrastructure available to me, 163 pilots, reflected broader institutional limitations in preparing personnel for fundamentally new operational demands. Flight simulators capable of replicating rocket motor characteristics did not exist, forcing pilots to develop essential skills during actual powered flights. Ground-based training systems could teach fuel system procedures, but could not prepare pilots for executing those procedures under high G acceleration. Emergency training relied on classroom instruction and static cockpit mock-ups, rather than dynamic simulation of crisis situations. Perhaps most significantly, the training doctrine emphasized individual skill development rather than systematic risk management approaches that might have compensated for human performance limitations. Pilots received extensive instruction on proper control techniques, but limited education about recognizing and managing the cognitive degradation that high-G flight produced. Ground crews learned fuel handling procedures, but received minimal training in the broader system dynamics that could transform minor procedural variations into catastrophic failures. Safety culture within the test program reflected military aviation's traditional acceptance of high-risk operations in pursuit of combat effectiveness. Incident reporting focused on mechanical failures and obvious procedural violations rather than systematic analysis of human factors' contributions to operational problems. Near-miss events often went undocumented if they did not result in visible damage or injury. The organizational pressure to maintain flight test schedules discouraged detailed investigation of incidents that might reveal systemic safety problems requiring program delays. This institutional approach to safety management created conditions where human factors problems could accumulate without triggering corrective action. Individual pilot or ground crew errors were typically attributed to insufficient training or experience rather than recognition that the operational environment exceeded normal human performance capabilities. The absence of systematic data collection about human factors incidents meant that patterns indicating fundamental design problems remained invisible to program management. Medical support systems reflected similar gaps in understanding the physiological demands rocket aircraft operations created. Flight surgeons possessed extensive experience with conventional aviation medicine, but limited knowledge of the physiological effects produced by sustained high-G acceleration or exposure to hypergolic fuel vapors. Medical protocols for handling fuel contamination injuries were rudimentary, often relying on general chemical exposure treatments rather than procedures specific to hydrazine or high-concentration hydrogen peroxide exposure. The cumulative effect of these human factors deficiencies created operational conditions where competent, experienced personnel consistently performed below the standards necessary for safe rocket aircraft operations. The system demanded perfection while providing conditions that systematically degraded human performance below optimal levels. Each flight represented a convergence of multiple risk factors that training and experience could mitigate but never eliminate entirely. December 31, 2025, the transition from theoretical design to operational reality began with seemingly routine events that gradually revealed the fundamental incompatibilities embedded within the Me-163 feat's design philosophy. On February 13, 1941, during early powered flight testing at Peenemünde West, the Me-163 V4 prototype experienced what flight test records initially classified as a successful demonstration flight. Pilot Heini Dittmar executed a normal takeoff sequence, achieved the planned test altitude of 6,000 meters, and completed the prescribed flight profile within acceptable parameters. The Walter HWK-109-500, a rocket motor, functioned according to specifications, producing rated thrust levels and consuming fuel at predicted rates. All primary flight systems operated normally throughout the powered flight phase. The divergence between perceived success and actual system behavior became apparent only during the post-flight inspection phase. Ground crews discovered that the aircraft's fuel tank had sustained internal damage during the flight, with clear evidence of T-stoff decomposition occurring within the tank structure. The decomposition had generated sufficient heat and pressure to cause permanent deformation of internal tank components, though the structural integrity remained adequate for flight completion. Chemical analysis of residual fuel samples revealed contamination levels that significantly exceeded normal operational parameters, indicating that catalytic decomposition reactions had occurred throughout the flight. This incident established a pattern that would characterize the Me-163's entire operational history. Flights that appeared successful according to primary mission criteria often concealed serious system degradation that accumulated over multiple operational cycles. The aircraft's design philosophy prioritized immediate performance metrics over long-term system integrity, creating conditions where successful mission completion masked progressive system deterioration. Pilots and ground crews developed operational procedures based on immediately observable aircraft behavior, unaware that the fuel system was experiencing continuous chemical degradation that eventually would produce catastrophic failures. The unpowered landing phase represented the most visible manifestation of design assumptions that conflicted with operational realities. The Me-163's limited fuel capacity necessitated unpowered approaches after fuel exhaustion, transforming every landing into a precision gliding exercise with minimal margin for error. Unlike conventional gliders designed specifically for unpowered flight, the Me-163's aerodynamic characteristics were optimized for high-speed powered flight, producing glide ratios and control responses that challenged even experienced pilots. The approach profile demanded precise energy management techniques that differed fundamentally from conventional powered aircraft procedures. Pilots had to establish correct approach geometry, while the aircraft retained significant kinetic energy from its high-speed flight phase, requiring accurate judgment of approach angles and touchdown speeds that provided no opportunity for powered correction. The aircraft's swept-wing configuration produced handling characteristics during slow-speed flight that were unfamiliar to pilots trained on conventional aircraft, with control effectiveness that varied significantly across the approach speed range. Landing gear design amplified the precision requirements of the approach phase. The retractable skid system eliminated the shock absorption capability provided by conventional landing gear, demanding touchdown attitudes within extremely narrow tolerances. Excessive approach speeds could cause skid system failure or loss of directional control during ground roll. Insufficient approach speed could result in hard touchdowns that damaged aircraft structure or caused fuel system ruptures. The skid configuration provided no capability for directional control during ground operations, making crosswind landings particularly hazardous. Weather conditions significantly affected landing success probability in ways that flight test programs could not fully evaluate. Runway surface conditions influenced skid system performance characteristics that had been established only under ideal testing circumstances. Crosswind components that would be manageable in conventional aircraft often exceeded the Me-163 feet's control authority during ground operations. Visibility restrictions during approach phases eliminated visual reference points that pilots required for accurate energy management and touchdown attitude control. The fuel jettison system introduced additional complexity into landing operations that often created new hazards while attempting to reduce others. Emergency fuel dumping could reduce fire risk in case of landing accidents, but the jettison process itself created chemical contamination around airfield facilities. Incomplete fuel jettison left residual quantities sufficient for explosion while dispersing toxic vapors across operational areas. The jettison procedure required precise timing relative to approach geometry, adding procedural complexity during phases when pilot workload was already at maximum levels. Ground proximity during approach phases created unique hazards related to fuel system behavior under stress. The aircraft's high approach speeds compressed the time available for emergency decision-making should system problems develop during final approach. Engine restart was impossible after fuel exhaustion, eliminating the go-around capability that provided safety margins in conventional aircraft operations. Emergency landing procedures required immediate recognition of system problems and rapid execution of complex emergency checklists, while maintaining aircraft control during rapidly changing flight conditions. The communication requirements during landing operations revealed systematic gaps in operational coordination protocols. Ground control procedures developed for conventional aircraft provided inadequate support for managing the unique hazards that rocket aircraft operations created. Emergency response capabilities at most airfields were unsuitable for handling hypergolic fuel fires or chemical contamination incidents. Medical facilities lacked appropriate treatments for hydrazine or hydrogen peroxide exposure, creating additional risks for personnel involved in emergency response operations. Flight test data from this period documented a disturbing pattern of incidents that individually appeared minor but collectively indicated fundamental system problems. Landing system failures occurred at rates significantly higher than comparable conventional aircraft. Fuel system anomalies appeared regularly but were often attributed to operational factors rather than design deficiencies. Pilot reports described handling characteristics that deviated from predicted performance, particularly during high-stress operational phases. The organizational response to these accumulating problems reflected institutional biases that prioritized program continuity over systematic safety analysis. Individual incidents typically triggered specific procedural modifications rather than broader evaluation of design assumptions. Technical problems were addressed through equipment refinements rather than fundamental reconsideration of operational concepts. The pressure to maintain flight test schedules discouraged detailed investigation of incidents that might reveal systemic problems requiring major program revisions. Perhaps most significantly, the definition of successful operations gradually shifted to accommodate system behavior that would have been considered unacceptable during initial design phases. Landing incidents that damaged aircraft structure became routine rather than exceptional events. Fuel system contamination levels that originally triggered extensive investigation became accepted as normal operational variation. Performance degradation that initially prompted design reviews became incorporated into standard operating procedures. This normalization of deviance created conditions where serious system problems became invisible to routine operational oversight. The gradual erosion of safety margins occurred slowly enough that each individual step seemed reasonable, while the cumulative effect fundamentally altered the risk profile of aircraft operations. Personnel adapted to increasingly demanding operational conditions without recognizing that the adaptation process itself indicated fundamental design inadequacies. Weather impacts on operations revealed another category of design assumptions that proved inadequate under real-world conditions. The Me-163's performance characteristics had been established primarily under ideal atmospheric conditions, with limited evaluation of degraded weather impacts on critical operational phases. Rain, snow, or ice formation could affect fuel system function in ways not anticipated during clear weather testing. Temperature extremes influenced chemical stability of propellants and effectiveness of fuel handling equipment. Maintenance requirements between flights created additional operational constraints that interfered with mission-ready aircraft availability. The complex fuel system purging procedures required extensive time and specialized equipment, limiting the frequency of flight operations. Chemical contamination of maintenance areas created ongoing health hazards for ground personnel and required specialized cleanup procedures that delayed subsequent operations. Equipment degradation from chemical exposure occurred more rapidly than anticipated, increasing maintenance workload and parts replacement requirements. The cumulative operational experience during this phase demonstrated that the Me-163's design created conditions where normal aviation safety principles could not function effectively. The aircraft demanded levels of precision and reliability that exceeded typical operational capabilities while providing operational conditions that systematically degraded precision and reliability. Each flight represented a convergence of multiple risk factors that could be managed individually but became unmanageable when they occurred simultaneously, as they inevitably did during routine operations. December 31, 2025. The chemical reactions occurring within the Me-163's fuel system during operational phases created failure mechanisms that transcended conventional aircraft safety analysis frameworks. Post-shutdown fuel system behavior revealed the fundamental inadequacy of design assumptions about propellant chemistry management under real-world conditions. Residual T-STOF and C-STOF quantities remaining in fuel lines and engine components after normal flight operations continued active decomposition reactions that generated heat, pressure, and toxic vapors for extended periods after engine shutdown. Chemical analysis of fuel system components recovered from aircraft incidents documented the progressive nature of these decomposition processes. T-STOF decomposition produced superheated steam and oxygen at pressures sufficient to rupture fuel lines designed to contain normal operating pressures. The decomposition rate accelerated in the presence of catalytic materials commonly found in aircraft construction, including copper fittings, iron components, and organic sealants used in fuel system assembly. Once decomposition began, the reaction became self-sustaining and could not be terminated through conventional fuel system purging procedures. C-STOF presented different but equally serious chemical hazards that persisted after flight operations. Hydrazine components formed explosive vapor concentrations when spilled or incompletely purged from fuel lines. The methanol constituents created fire hazards when exposed to ignition sources during maintenance operations. Copper catalyst particles could accumulate in fuel system components, creating contamination that triggered accelerated decomposition in subsequent flights. The combination of these chemical processes meant that aircraft remained dangerous for maintenance personnel, hours, or even days after flight operations concluded. Temperature effects on fuel chemistry created additional failure pathways that had not been anticipated during initial design phases. High-altitude flight exposed fuel systems to temperature extremes that altered chemical stability characteristics of both propellants. Rapid temperature changes during ascent and descent created thermal stress in fuel system components that could open leak paths for propellant seepage. Solar heating of aircraft during ground operations could raise fuel temperatures above safe handling limits, particularly for T-STOF, which became increasingly unstable as temperatures increased. The engine combustion chamber itself became a source of ongoing chemical hazards after shutdown. Residual propellant deposits on combustion chamber walls continued decomposition reactions that generated heat and pressure within the closed engine compartment. These reactions could produce sufficient energy to damage engine components or ignite external fuel vapors if aircraft maintenance was attempted too soon after flight operations. The lack of adequate cooling systems for post-shutdown thermal management meant that aircraft required extended cooling periods before safe maintenance could begin. Vibration effects during flight operations accelerated fuel system degradation through mechanisms that static testing could not evaluate. Engine vibration transmitted through aircraft structure created stress concentrations in fuel line connections and tank mountings that gradually loosened fittings designed for static pressure loads. Control surface deflections during maneuvering generated structural loads that affected fuel system alignment and created new stress patterns in fuel line routing. Landing impacts transmitted shock loads through the aircraft structure that could damage fuel system components previously weakened by chemical exposure or thermal cycling. The autopsy of failed fuel system components revealed systematic material degradation that occurred much more rapidly than design specifications predicted. Aluminum components exposed to T-STOF showed corrosion patterns indicating chemical attack that accelerated under operational stress conditions. Rubber seals and gaskets deteriorated rapidly when exposed to C-STOF vapors, losing elasticity and developing leak paths that allowed propellant mixing. Metal fuel lines showed evidence of internal surface roughening that created nucleation sites for decomposition reactions and increased pressure loss during normal operations. Documentation from post-incident investigations revealed that fuel system failures often followed predictable patterns that could have been recognized if appropriate monitoring systems had been available. Initial contamination events typically produced subtle changes in fuel flow characteristics or pressure readings that were within normal operational variation ranges. These early indicators were masked by the normal variations in rocket motor performance and were not recognized as precursors to serious system problems. The progression from initial contamination to catastrophic failure typically occurred over multiple flight cycles, with each operational sequence adding incremental damage that eventually exceeded system tolerance limits. T-STOF contamination would begin with trace amounts of catalytic material introduced during fuel loading or maintenance operations. The contamination would trigger localized decomposition reactions during subsequent flights, generating heat and pressure that stressed nearby components. Repeated exposure to these stress cycles gradually weakened fuel system integrity until catastrophic failure became inevitable. C-STOF contamination followed different failure progression patterns but produced equally predictable results. Hydrazine exposure to atmospheric moisture created corrosive compounds that attacked metal fuel system components. The corrosion process accelerated under flight stress conditions, particularly during high-G maneuvering that increased mechanical loads on already weakened components. Methanol vapors could accumulate in enclosed spaces within the aircraft structure, creating explosive atmospheres that could be ignited by electrical systems or mechanical sparks during maintenance operations. The interaction between different failure modes created compounding effects that exceeded the sum of individual failure probabilities. Fuel system leaks could expose aircraft structure to chemical attack, weakening mounting points and creating new vibration sources that accelerated further degradation. Electrical system contamination from fuel vapors could cause instrumentation failures that prevented recognition of developing fuel system problems. Fire suppression system activation during fuel-related emergencies could spread contamination throughout aircraft systems previously unaffected by propellant exposure. Post-flight inspection procedures proved inadequate for detecting the chemical degradation processes occurring within fuel systems. Visual inspection could identify obvious damage such as burned or corroded components, but could not detect the molecular-level changes that preceded visible damage. Pressure testing could verify gross system integrity, but could not identify developing leak paths or contamination that had not yet progressed to failure. Chemical analysis of fuel samples could detect some contamination types, but required laboratory facilities and analysis time that were not available for routine operational support. The time delay between cause and effect in fuel system degradation created particular challenges for maintenance decision-making. Contamination introduced during one flight might not manifest as visible damage until several subsequent flights had occurred. This delay made it difficult to correlate specific operational events with later system failures, preventing effective modification of procedures that might prevent similar problems. Maintenance personnel often worked on aircraft without realizing that previous flight operations had initiated chemical processes that made current maintenance operations hazardous. Environmental factors significantly amplified chemical degradation rates in ways that laboratory testing had not predicted. Humidity levels affected T-stop stability and accelerated corrosion of metal components exposed to fuel vapors. Temperature cycling between ground operations and high-altitude flight created thermal stress that opened new leak paths and accelerated chemical reactions. Atmospheric pressure changes during flight operations affected vapor concentrations within aircraft structures and influenced the distribution of toxic atmospheres during maintenance operations. The chemical contamination of airfield facilities created additional operational hazards that extended beyond individual aircraft. Fuel spills during loading operations left residual contamination that could affect subsequent aircraft operations. Ground equipment exposed to hypergolic fuel vapors experienced accelerated corrosion that reduced reliability and created new failure modes. Maintenance facilities became progressively more contaminated over time, creating cumulative health hazards for personnel and increasing fire risks for all operations conducted in those facilities. Perhaps most critically, the chemical reactions occurring within Mi-163 fuel systems violated fundamental assumptions about aviation system behavior that underpinned all conventional safety analysis methods. Traditional aviation safety analysis assumed that aircraft systems became safer as operational experience accumulated and procedures were refined. The Mi-163's chemical systems became more dangerous over time, with each operational cycle adding contamination and degradation that increased failure probability for subsequent operations. This inversion of normal safety trends made it impossible to establish stable operational procedures or to develop meaningful safety margins through experience. The emergency procedures developed for managing Mi-163 fuel system crises inadvertently created new categories of hazards that often exceeded the risks they were designed to mitigate. Fuel jettison systems, intended to reduce fire and explosion risks during emergency landing situations, dispersed hypergolic chemicals across airfield environments in patterns that created persistent contamination zones dangerous to personnel and equipment. The chemical dispersion characteristics of emergency fuel dumps had not been systematically analyzed during design phases, leaving operational personnel without adequate understanding of safe exposure limits or effective decontamination procedures. Emergency fuel jettison during flight operations created unique aerodynamic and chemical hazards that conventional emergency procedures could not address effectively. The jettison process required opening multiple fuel system valves simultaneously while maintaining aircraft control under potentially degraded conditions. T-stop and C-stop ejected at high airspeeds formed vapor clouds that could extend several kilometers downwind from the aircraft, creating toxic exposure hazards for ground personnel and other aircraft operating in the vicinity. The chemical persistence of these vapor clouds exceeded the duration of normal emergency response coordination, leaving contaminated airspace that remained dangerous for extended periods. Ground contamination from emergency fuel dumps created operational problems that accumulated over multiple incidents. Hypergolic propellant soaking into runway surfaces and surrounding soil created chemical reaction zones that generated toxic vapors whenever disturbed by aircraft operations or maintenance activities. Standard airfield decontamination procedures proved inadequate for neutralizing hypergolic contamination, often spreading contamination rather than eliminating it. Specialized chemical disposal procedures required equipment and expertise that were not available at most operational airfields, leaving contaminated areas that posed ongoing health and safety risks. The incomplete nature of emergency fuel jettison created additional hazards that often proved more dangerous than complete fuel retention. Partial fuel dumps left residual quantities of T-stuff and C-stuff in fuel system components, but in proportions that could not be predicted or controlled. These residual quantities were sufficient to produce explosive reactions if accidentally mixed during post-emergency maintenance, but were too small to be effectively purged using standard fuel system cleaning procedures. Personnel working on aircraft after emergency fuel jettison faced unknown contamination levels that could not be measured using available detection equipment. Fire suppression systems designed for conventional aircraft proved not only ineffective against hypergolic fuel fires, but often made them worse by spreading burning propellants across wider areas. Water-based suppression systems accelerated T-stuff decomposition reactions, creating steam explosions that dispersed burning chemicals over larger areas. Carbon dioxide systems provided insufficient cooling capacity to stop hypergolic combustion reactions, which generated their own oxidizer and could continue burning in oxygen-depleted atmospheres. Foam suppression systems were rapidly destroyed by the chemical action of burning hypergolic propellants, providing only momentary suppression before fire breakthrough occurred. Medical response protocols for hypergolic fuel exposure revealed fundamental gaps in understanding the physiological effects of these chemicals. Hydrazine exposure produced symptoms that could be delayed for hours after initial contact, making it difficult to correlate exposure events with medical problems. High-concentration hydrogen peroxide caused severe chemical burns that progressed rapidly and could not be treated effectively using conventional burn therapy. The toxic vapors produced by hypergolic reactions could cause respiratory damage that was not immediately apparent but became life-threatening within hours of exposure. Personnel protective equipment available to ground crews and emergency responders proved inadequate for the chemical environment that Mi-163 operations created. Standard aviation protective clothing offered minimal protection against hypergolic chemical exposure. Respiratory protection equipment designed for conventional aviation hazards could not filter the toxic vapors produced by hypergolic reactions. Eye protection that was adequate for normal maintenance operations provided insufficient protection against hypergolic vapor exposure, which could cause permanent vision damage even at low concentrations. The coordination of emergency response activities became extremely complex when multiple agencies had to operate in chemically contaminated environments. Fire departments typically lacked training and equipment for dealing with hypergolic fuel incidents. Medical personnel were unfamiliar with treatment protocols for hydrazine or high-concentration hydrogen peroxide exposure. Military security requirements often prevented civilian emergency responders from accessing incident sites, forcing reliance on military personnel who lacked specialized chemical emergency training. Weather conditions significantly affected the success of emergency response operations and the extent of chemical contamination spread. Wind patterns determined vapor dispersion characteristics that could not be predicted in advance of actual incidents. Rain or snow could accelerate chemical decomposition processes and create runoff contamination that spread far beyond initial incident sites. Temperature extremes affected the volatility of spilled chemicals and the effectiveness of available protective equipment. Communication during chemical emergencies proved particularly challenging due to the need for specialized terminology and the urgency of rapid response requirements. Radio protocols developed for conventional aviation emergencies did not include appropriate procedures for describing chemical contamination characteristics or coordinating multi-agency responses to toxic vapor incidents. The technical complexity of hypergolic chemistry made it difficult for emergency coordinators to understand the actual hazards present or to communicate appropriate protective measures to responding personnel. Recovery operations after emergency incidents often proved more hazardous and time-consuming than the original emergency itself. Aircraft that had experienced fuel system emergencies required specialized decontamination procedures before normal maintenance could resume. Ground areas contaminated by fuel spills needed extensive remediation using techniques that were still being developed as experience with hypergolic incidents accumulated. Equipment that had been exposed to hypergolic vapors often suffered accelerated corrosion that was not apparent until weeks or months after the exposure occurred. The psychological effects of working in chemically hazardous environments created additional operational problems that interfered with emergency response effectiveness. Personnel who had experienced hypergolic exposure incidents often developed heightened sensitivity to chemical odors and became reluctant to work around aircraft that might contain fuel system contamination. The knowledge that minor procedural errors could result in serious chemical exposure created stress levels that interfered with normal decision-making processes during emergency situations. Training for chemical emergency response proved difficult to accomplish realistically without creating actual hazardous conditions. Simulator training could teach theoretical procedures, but could not prepare personnel for the physical and psychological stress of working in toxic environments while wearing protective equipment. Live training exercises using actual hypergolic chemicals were too dangerous to conduct safely, leaving personnel without realistic preparation for actual emergency conditions. Investigation of emergency incidents was complicated by the chemical contamination that often destroyed physical evidence before it could be analyzed. Chemical reactions continued after incident conclusion, altering the physical evidence that investigators needed to determine cause and effect relationships. Photography and documentation of incident sites had to be conducted by personnel wearing protective equipment, limiting the quality and completeness of evidence collection. Laboratory analysis of contaminated components required specialized facilities that were not readily available. Perhaps most troubling, the accumulation of emergency incidents revealed that the risk mitigation strategies embedded in Mi-163 design actually amplified total system risk rather than reducing it. Each emergency procedure created new hazard categories that required additional emergency procedures, creating cascading complexity that eventually became unmanageable. The chemical properties that made emergency situations so dangerous also made emergency response so hazardous that personnel safety during response operations often exceeded the original emergency risks. The organizational learning process from emergency incidents was systematically impeded by the chemical contamination problems that each incident created. Post-incident analysis required extensive decontamination delays that degraded the quality of physical evidence and personnel recollections. The health hazards associated with incident investigation limited the thoroughness of analysis that could be safely accomplished. The ongoing contamination problems created by each incident absorbed organizational resources that might otherwise have been applied to systematic safety analysis and improvement. The long-term operational data from Mi-163 squadrons revealed statistical patterns that contradicted fundamental assumptions about risk reduction through operational experience and procedural refinement. Aircraft loss rates remained consistently high throughout the program's operational life, showing no significant improvement despite accumulated flight hours, refined procedures, and enhanced pilot training. More significantly, detailed analysis of loss causes demonstrated that fuel system to related incidents correlated directly with cumulative operational exposure, rather than pilot experience levels or procedural compliance rates. Statistical analysis of Jag-Geschwader 400 operations, conducted using squadron records maintained throughout the unit's active period, documented 279 aircraft losses from all causes during approximately 18 months of operational activity. Of these losses, 114 were directly attributed to fuel system failures occurring during ground operations, takeoff, landing, or post-flight maintenance activities, An additional 67 losses involved fuel system complications as contributing factors, even when primary cause attribution was assigned to other failure categories. This meant that fuel system problems played a role in nearly 65% of all aircraft losses, far exceeding the statistical contribution of combat damage, pilot error, or mechanical failure of other aircraft systems. Chemical forensics conducted on recovered aircraft components provided objective evidence of the progressive degradation processes that made each successive flight more dangerous than the previous one. Fuel tank examinations revealed cumulative chemical damage that accelerated with operational exposure, regardless of maintenance quality or fuel handling procedures. Internal tank surfaces showed progressive corrosion patterns that created increasingly rough textures, providing nucleation sites for decomposition reactions that accelerated fuel degradation during subsequent operations. Fuel line components displayed systematic material property changes that reduced pressure tolerance and increased leak probability over operational lifespans that were measured in dozens of flight hours rather than the hundreds or thousands typical for conventional aircraft systems. Post-incident chemical analysis revealed contamination patterns that definitively established the role of residual propellants in creating ongoing hazards between operational flights. Samples taken from aircraft that had experienced minor fuel system incidents showed contamination levels that exceeded safe handling thresholds by orders of magnitude. Ground contamination analysis around maintenance areas documented chemical persistence that created toxic exposure hazards for weeks after aircraft operations concluded. Personnel exposure monitoring revealed cumulative chemical exposure levels that exceeded occupational safety standards even for individuals who followed all established protective procedures. The comparative analysis with conventional aircraft safety performance metrics demonstrated the fundamental inadequacy of applying normal aviation safety frameworks to rocket-powered aircraft operations. Conventional military aircraft of the same operational period typically achieved loss rates of 2 to 4 aircraft per 1,000 flight hours from all non-combat causes. Mi-163 operations experienced loss rates exceeding 50 aircraft per 1,000 flight hours from fuel system problems alone, representing more than a 10-fold increase in hazard levels that could not be attributed to normal operational risks or pilot inexperience. Maintenance cost analysis revealed economic unsustainability that extended beyond direct aircraft replacement expenses. Specialized facilities required for safe fuel system maintenance carried construction and operating costs that exceeded conventional maintenance infrastructure by factors of 5 to 10. Personnel training for safe hypergolic fuel handling required extensive specialized education that was not transferable to other aircraft types. Medical support infrastructure needed to handle chemical exposure incidents required capabilities that were not normally available at military airfields. The regulatory framework evolution during and after the Mi-163 program documented institutional recognition that existing aviation safety standards were inadequate for rocket-powered aircraft operations. Technical orders issued during operational deployment progressively restricted fuel handling procedures, limited operational flight profiles, and required additional safety equipment that ultimately made routine operations impractical. Post-war analysis by Allied technical intelligence teams characterized the Mi-163 as an example of technological advancement that exceeded safe operational implementation capability. Design philosophy lessons derived from comprehensive Mi-163 analysis influenced post-war rocket aircraft development programs by establishing principles that explicitly prioritized operational safety over theoretical performance capabilities. The X-1 and subsequent experimental rocket aircraft incorporated fuel systems that used less reactive propellant combinations, accepted performance penalties to achieve safer handling characteristics, and included extensive safety systems that the Mi-163's design had omitted. These design philosophy changes represented explicit recognition that the Mi-163's approach to trading safety for performance had proven fundamentally flawed. International aviation safety standards development during the 1950s incorporated specific provisions addressing rocket-powered aircraft that directly reflected lessons learned from Mi-163 operations. Requirements for non-toxic propellants, fail-safe fuel system designs, and comprehensive emergency response capabilities became mandatory for experimental aircraft certification. Personnel training standards for rocket aircraft operations were established at levels far exceeding those originally implemented for Mi-163 programs. Technology transfer attempts to civilian aviation applications revealed additional limitations of the Mi-163's technical approach. Proposed commercial applications of rocket propulsion for high-speed passenger transport were abandoned after safety analysis demonstrated that hypergolic fuel systems created unacceptable risks for civilian operations. Military transport applications were similarly rejected due to logistical complexity and personnel safety concerns that made operational deployment impractical. Academic analysis conducted decades after the Mi-163 program concluded provided theoretical frameworks for understanding why certain technological approaches create irreducible operational risks. Systems engineering analysis identified the Mi-163 as a classic example of normal accident theory, where complex systems create failure modes that cannot be eliminated through procedural improvements or operational experience. The aircraft demonstrated how pursuit of extreme performance capabilities can embed failure mechanisms that make routine operational deployment impossible. The medical research conducted on personnel who had experienced chronic exposure to hypergolic fuel systems documented long-term health effects that were not apparent during active operations. Follow-up studies of ground crews and maintenance personnel revealed significantly elevated rates of respiratory disease, skin conditions, and other health problems associated with chemical exposure. These findings provided additional evidence that the Mi-163's operational approach created unacceptable risks that extended far beyond immediate operational safety concerns. Environmental impact analysis of former Mi-163 operational sites revealed persistent soil and groundwater contamination that required extensive remediation decades after operations concluded. The chemical persistence of hypergolic propellants in environmental systems created cleanup costs that exceeded the original aircraft development expenses. Site remediation technology had to be specifically developed to address contamination types that had not existed before rocket aircraft operations began. Quality control analysis of Mi-163 production revealed systematic manufacturing problems that were directly attributable to the complexity of building aircraft systems designed to handle hypergolic chemicals safely. Production tolerances required for safe fuel system assembly exceeded normal aircraft manufacturing capabilities, resulting in inconsistent quality that created additional operational hazards. Manufacturing personnel experienced elevated injury rates and health problems associated with exposure to materials and processes required for rocket aircraft construction. Perhaps most significantly, comprehensive cost-benefit analysis demonstrated that the Mi-163's operational limitations prevented it from achieving any meaningful military objectives, despite its impressive theoretical capabilities. Combat effectiveness analysis showed that the aircraft's operational constraints limited mission profiles to circumstances where conventional interceptors would have been equally effective. The enormous resource investment in Mi-163 development and deployment produced no measurable improvement in defensive capabilities against Allied bomber operations. The institutional memory preservation efforts undertaken by post-war aviation organizations explicitly documented Mi-163 lessons to prevent repetition of similar technological approaches. Technical documentation standards were enhanced to ensure that safety-critical design decisions would be adequately recorded for future reference. Educational curricula for aerospace engineers incorporated specific case study material from Mi-163 development to illustrate the consequences of prioritizing performance over operational safety.